Welcome to the AP Atomic and Nuclear Physics Solutions to number 14 and 16 from the problem set. Let's get started right away with 14 here. They want us to calculate the average binding energy per nucleon of NB93 and AU197. We'll call the first problem here with NB. All right, the first thing we need to do is figure out the total mass of the nucleons that make up the NB nucleus. And it has an atomic number of 41. So there's 41 protons, which will be 41 times the atomic mass units of one proton, 1.007825. And when we multiply, and at any point during this video, if you need time to calculate, please pause the video to do so. I'm not going to keep repeating that. We get a total of 41.320825 atomic mass units. We also know that it has a mass number of 93, which is the total number of neutrons and protons. We take 93 and subtract 41, and we get from that there are 52 neutrons. So the mass of 52 neutrons would be 52 times the mass of one neutron, 0.008665 atomic mass units. And that gives us a total of 52.45058 atomic mass units. We now add that total amount of protons and neutrons together to get the total mass of the nucleons itself, and that's 93.771405 atomic mass units. We now go and look up NB on the chart, and you have a chart on your assignment sheet, and I have one here for reference. They should be similar. And we see that the actual mass of the NB nucleus is 92.9064 atomic mass units. So the mass of the sum of the parts is greater than the mass of the whole itself. We subtract that value to get our mass defect, which is 0.865005 atomic mass units. All right. Now that we know that, we can go ahead and calculate the binding energy by simply taking our mass defect, 0.865005 atomic mass units, which gets converted to energy to hold the nucleons together in the nucleus. And that's at 931 MeV per 1 atomic mass unit. Atomic mass units cancels, and we get a binding energy of 805 mega electron volts. One step further now, we want the binding energy per nucleon. We take the binding energy of 805 MeV, divide by the total number of nucleons, which in this case is the mass number, 93. And dividing, that gives us 8.66 MeV per nucleon. All right, so that's our first answer for NB. We now are asked to also do this for gold. So we'll do it again for AU. Repeat the same process. Gold has 79 protons. There's its atomic number, which is 79 times, again, the atomic mass of one proton, 1.007825. And that gives us a total of 79.618175 atomic mass units. All right, gold has a mass number of 197. So 197 minus 79 gives us 118 neutrons. So 118 times the mass of one neutron, 1.00, 8665, gives us a total of 119.02247 U. Add those two totals together to get the total mass of the nucleons, 198.640645. And now we go look up the actual mass of the gold nucleus, and we see that it is actually only 196.9665 atomic mass units. Subtract to get the mass defect, and that gives us 1.674145 atomic mass units. Now to get the binding energy, which we'll do over here to the right, we take that mass defect, 1.674145, multiplied by 931 MeV per 1 atomic mass unit, and we get a binding energy of 1,559 mega electron volts. Now we want the binding energy per nucleon. Simply bear our binding energy, 1,559, divide by the total number of nucleons, which in this case is 197, and that gives us a binding energy per nucleon of 7.91 MeV per nucleon. What's interesting to note here is notice from the lesson, what we talked about is that once you get past iron, the larger the atom, the less stable it is. This is proved in this case. Nb only has 93 nucleons, gold has 197 nucleons, and you see that gold is a less stable, has less binding energy per nucleon than Nb did. All right, now to 16. We're asked to complete the following radioactive decay formulas. These are all look to be natural transmutations, because we have an element decaying into another element plus a radioactive particle. So for A, we have bismuth 212 decays into something plus an alpha particle, which we recognize as the helium nucleus there. Alpha particle. All right, really easy here. What plus 2 gives us 83, and that would be an atomic number of 81. And what plus 4 gives us 212, and that would be a mass number of 208. We go to a periodic table or some other chart. There's one above here. You go to the slide back in the video a little bit, and we look up what has the atomic number of 81, and that is TL, which is thallium. Okay? All right, so there's A. B, we have krypton 95. Which naturally decays into some element plus the beta particle. And the beta particle is a high-speed electron, mass number 0, atomic number -1. What plus -1 gives 36? And that would be 37. And what plus 0 is 95? Of course, is 95. we go up and look at our chart or a periodic table for what element has the atomic number 37, and that's Rb, which is rubidium. Okay? And for C, we have some element that decays into cesium-140 plus an alpha particle. Doesn't matter the order that you write them in. So what was the original element? 58 plus 2 is 60, so our unknown element has an atomic number of 60 and a mass number of 140 plus 4, so 144. We go up and find, using a periodic table or other chart, what has an atomic number of 60, and we see that it's Nd, which is neodymium. All right, and that'll do it for the solutions to 14 and 16. More to come in class.